Hello. Hello. Yes, Adarsh. Oh my god, এখন তো একই প্রবলেম আসছে। So what to do now? What a problem, man. I have no idea now. Hello. এবার তো কাজ করছে। So এটার মিট লিঙ্কটা কপি কর, কপি লিঙ্ক অ্যাড্রেস মজিলা খুলে এবার। অপেরা মাথায় আসছে না কি করবো। What a bad day, man. Technical error. Finally able to access, guys. Okay, let's start now. Call. You are able to hear, right? This time. Hello.
Yes, sir. Yes, sir.
Finally, I had to change the web browser as well. Chrome was not working, I think. It's an Opera. Okay, let's get started now. Finally. Call everybody here on Google Chrome, Google Meet only. Okay. 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 So, uh, able to hear now, right? Hello. Able. Okay.
Yes, sir. Can
Okay. Okay. Let's get started. Linear discriminant. Previously, we have covered logistic regression. We have seen the loss function of that logistic regression, which is of the form of the Bernoulli distribution. We took the log of that, and optimizing that will get to the uh, we'll get to the classifier, we'll get to the discriminant. Okay, now acha, very low. Now okay. Okay now. uh, able to hear? Yes, end the zoom one. Eh, volume is good now. Volume is good.
Yes, yes, sir.
Good, right? Okay. Okay, let's continue. So the idea of the linear discriminant analysis is to find a it helps in reducing the dimension of the data, and also make the data more separable. Okay, so this is an example I have come up with, in which there is suppose uh, means like a person has a disease. Okay, and suppose the gene X we are looking at, suppose first that. So if it is at low quantity, the green ones are the sample, which shows that it has no the person has no disease. And if we, as the concentration of the gene increases, the person is having disease. Okay, uh, so like gene
Like gene.
hello,
Hello,
my voice is repeating
my
to
voice
me.
is repeating to me.
What type of problem?
Type
You're
of problem.
you're
You're
able to
you're
hear?
able to hear?
Hello, you're able
Hello,
to hear?
you're able to hear?
Oh, now
Yes, sir.
okay, okay.
Sir, we cannot see the screen, sir.
Uh,
Uh,
yes, yes.
yes, yes.
Now able to see?
Now
Please,
able to
please.
see?
No, sir.
Not able to see now.
Not able to see now.
No, sir.
Uh,
Uh,
Now it's visible.
acha, acha,
Speechable, it's
acha,
speechable.
acha.
acha. Means it is coming
Acha,
Uh,
late.
means it's
Okay.
coming late. Okay.
Some lag is there.
I'm not getting it, sir. I do not know why.
Okay, okay.
Okay, okay.
So
So,
the
the
idea is that
idea is that
you're having gene
you're having
X,
gene X,
like less
like
quantity
less
of that,
quantity of
so
that,
has no
so has
diseases.
no disease.
And if the quantity increases, that person is having disease. The samples are
Okay,
like
sir.
that.
Okay, huh, sir.
Having
Okay,
disease. The samples are like that.
voice is echoing, right?
Voice going right.
Sir, can I ask you a question for the assignment 4, the question number 1, how to solve the problem, sir?
Yes, it is part of the
Yes,
SVM.
it is part of the SVM.
Voice is still echoing, huh?
Acha.
Voice is still going. Eh?
It is going out, sir.
Uh, what can
Uh,
I do now?
what can I do now?
Oh,
Oh,
Sir, at first we will solve the problem, sir. It will be better, sir. Sir, nothing we can listen, sir.
okay, okay now, right?
all right.
Sir, now we can get your voice.
Okay, okay. Let's continue. Actually, lot
Okay,
of
okay.
problem.
Let's continue. Actually, lot of problem.
Uh,
Sir, at first, let's solve the sir assignment problem, sir. We are not. I am not getting, sir, all the problems, sir. Please.
that understand that SVM is not will not be easy to
That
understand out of
understand that SVM is not will not be easy to understand
means the
out of
videos are also not that
means the
good actually.
videos are also not that good
I
actually.
will quickly
No, it
cover.
is not a problem, sir.
We'll
Please.
quickly cover.
If we can solve the problems, then it will be very beneficial for us, sir.
No, if you don't understand how you'll solve
No,
means
if
like
you don't understand how it's solved, means like
No, please, sir. Please, sir, continue.
okay. So means like I'm
so
running little behind.
means like I'm
Uh,
running
so
little
linear
behind.
discriminant
Okay.
analysis.
So
Okay.
linear discriminant
Uh,
analysis. Okay.
So so this gene
So
X and gene Y
so
both
this
are
gene
there.
X and gene
Okay.
Y both are there.
So
Okay.
we are trying to find a plane
So we are trying to find a plane
along which it is clearly
along which
separable.
it is clearly separable.
If if I
If I
stop the
stop the
hello, don't means like talk now. Yes, it is better, right? Yes. Okay, okay, okay. Yes, it is working now. No echo, right? Yes. Please write in the chat.
Yes, sir.
Okay.
Yes.
Okay.
Yes.
Yes. Mute everyone. Okay. Maybe I'll use the controls here. Mm, okay. Where is the controls here?
Sir, are you the professor of IIT, sir? IIT Madras?
No, no.
no,
IIT Delhi, IIT Delhi.
IIT Delhi.
IIT Delhi.
Okay.
Professor there, sir?
Okay.
Just please
With
unmute.
please
Please mute
unmute.
actually.
Please mute actually.
It's like uh, and controls are not there now. Acha, here it is there. Okay. Okay. Wait a minute. What a problem. Okay, okay. Let's continue. Please don't unmute. Actually, write in the chat. Okay. Uh, so um, so this is linear discriminant analysis in which we are looking for a uh, direction or a hyperplane along which it is separable as well as means better separable. Okay. So as I was telling, these are the uh, two dimensions I have, x and y, and I am trying to find a plane on which these are better separable. Okay. So and also understand that if I'm trying to find a plane, right, this line 1D line. Okay. So what happens is like I'm also reducing the dimension from 2 to 1, right? And also you can understand if suppose the dimension is too large, like 10 dimensions, we cannot plot that one. Okay. I'm actually giving some intuition because in the videos there is no intuition, so it is very hard to understand what is the purpose of this linear discriminant analysis. Okay. So for reducing the dimensions, and in that reduced dimension it should be better separable. Okay, as you can see in 1D, this green and red are better separable. Okay. So you can understand, like if I draw a plane here, okay, and project onto this plane, then these are best separable, right? As you can understand. So so that is what here it is shown. This is a plane and we project into this plane to get into a lower dimension. Audio not working. Others are able to hear?
Sir, what are you walking, sir?
Okay, 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 okay. Let's continue then. And so this so the idea is here means in the videos this part of the LDA is better focused, in which like there is a prior and this is fx is the likelihood, and we are trying to find the probability of a occurrence of a class given the data. Okay, but this part is also in the later part of the video, uh, which is actually more important. So uh, if you look at this question here, yeah, so this is called the Fisher information result, this ratio. Okay, so the idea is that we try to find such a plane in which this mu's, the distance between the mu, that is the mean of the data of one type of data and mu of another type of data, is as large as possible, and the scatter, that is measured by the standard deviation, sum of that is as low as possible. Okay, so this is called the Fisher information result. Okay, so we're trying to maximize it. Okay, and that is what is our that is what will make it better separable. Okay, so and if you get to this, okay, the into the lectures videos that you have, okay, so there will find that means the one type of intuition is that we are trying to find the probability of occurrence of the class G with respect to the data. Okay, so for that we use Bayes theorem here. Okay, which is which is uh, which is the prior times likelihood, okay, divided by evidence. Okay, so okay, so with Bayes theorem, you know, right? You can write in the chat, don't unmute. Okay, audio is low. Bayes theorem, you know, right? Okay, let me show you. Okay, with a better one. Bayes theorem. Okay, so Bayes theorem, as you can see, this is has come. Okay, let's see.
What's the question, please?
The idea is that means like as I was saying, for this probability, that is the probability of the class with respect to the data, we need to use the Bayes theorem such that we are using this likelihood. Okay, likelihood of the data is known, multiplies the prior probability divided by this product of all the classes. Okay, this is the Bayes theorem. Okay, and well, I was trying to show is, where is it gone? Yeah, so uh, so this is called the posterior. Okay, yeah, equals to likelihood times prior divided by evidence. So now this is the Bayes theorem. Okay, so A is our class probability here, and B is the data we have. Okay, the opposite of that, probability of data with respect to class, that is the likelihood here. PA is the prior and PB is the evidence. Okay, okay, so let's continue. Okay, so we do this. Okay, the detailed derivation is there. Okay, and the assumption of this what do you call this linear discriminant analysis is this likelihood is Gaussian. Okay, this fx for k k subscript. Okay. So this was the question of the doubt previously. Oh. So as you can see, this fx subscript k is the that is the likelihood is given, and this pi 1 2 3 are the prior probability. Okay, and the you must understand here, like for every class the sum is going to be same, sum at the bottom is going to be same. Okay, and it is same because the, like for every class this product is going to be added. Okay, so the important part is this prior times likelihood, okay, which we are going to compare here. So as you can see, if the three classes have equal priors, the prediction must be class 2. So as you can understand here, this if this prior is same, then the probability of occurrence of the class depends on this likelihood only. Okay, so if the priors are same, then which have the maximum likelihood will give the will be the prediction. Okay, so as 0.2 is the highest, the prediction will be k equals to 2. Okay, so this is the class 2. Okay, so and on to the second option, as you will see, uh, the pi 2, that prior is maximum. Okay, so if you see that likelihood also 2 is maximum, pi is also maximum, so the probability will be maximum in case of class 2. Okay, so may not be necessarily, that is wrong, it should be in class 2. Okay, so this is the option. Okay, this is not. Next we come to as you can see, pi 1 is double. Okay, you can see that uh, yes, so pi 1 is greater than double. Okay, so if you multiply here 0.15 multiplied 2 is 3. Okay, so okay, for the equal case, okay, that double case I'm looking at. Okay, so this is 0.3 and this is 0.2. So for even the equal case, the pi 1 is, means like the probability of the class 1 is much large. You can see that. Okay, so but here it is given that it is even more than that. Okay, so probability of occurrence of class 1 is much greater than class 2. Okay, that should be clear, right? But we don't know any information about class 3. Okay, prior of the class 3, so it could be class 1 or class 3, it cannot be class 2 because class 2 is much lower than class 1. Okay, so this is the answer. And if pi 1 greater than pi 2 greater than pi 3, then prediction must be class 1. Nothing like that, means the ratios have to be known.
But it can't be in
Okay.
the last option which you checked, no? If pi 1 greater than 2 pi 2, the prediction will definitely be pi 1, class 1 only, no? Not class 3, because class 3's fx is very small. It's only 0.05.
It acha, say at the third point.
Yes, the third point.
Okay, so the thing is that means like fx is very small, but the prior is not known, right? Prior can be quite high. Okay, prior can be high, right? Means suppose that pi 1 is greater than suppose pi 1 here is 3 pi 2. Okay, and so how much that becomes 3 times, right? So that will be 0.445. Okay, and this is 0.2, and this can be like suppose pi 3 can be uh, 0.9 times pi 2. Okay, so then this can be equal, right? Class 1 and 3 will be equal. If suppose little bit more than 0.95, then not 0.95, I'm talking about 9 pi 2. Okay, I'm just giving you example. Okay, let me write it down. So what I'm saying is pi 1, suppose 3 pi 2. Okay, and pi 3 is 9.59, suppose. So what will happen, that the probability of class 1 is like 0.45 times class not 0.45, means like this product will become 0.45. Okay, 0.45 pi into fx. Okay, no, pi into uh, this is just pi 2. Okay, 0.45 pi 2. Okay, and then this will become 0.2 pi 2. Okay, and this will become 0.45 pi 2. Okay, so this
Point
is,
is understood. Your point is understood. Pi 3 is not given, so it can be.
yeah, that's it. So that was also done. Second, last part is also like that. 8 question is very simple, and that is our assumption. For LDA it has to be, for LDA it has to be Gaussian. Okay, okay, and as you see this question here, please mute this one, mute your voice. Okay, and okay, so um so what is the most appropriate line for projection? As you can see, this blue line is the one along which the data will be well separated. Means from this projection into this plane, you can see that they are clearly separable. Okay, so very simple question. And
Even the green line is quite good, no, for separation. Even if you project on the green line.
okay, so into the green line, what happens is, it does well, right? So, well, both are good. Okay, but in this case, what will happen is, we'll have to green can also be the answer, right? In this case,
Yeah.
uh, means without any data, it is like hard to ascertain. So question is like that only. What can I do? It's from previous year question.
Okay, let's move on.
Okay, and so this is actually quite different from what we have learned here, but still easy enough. Okay, so the number of features of the logistics regression, if is more than the data set, what will happen, that it will overfit. Okay, and it is due to the fact that uh, let me explain. So the idea is this, like means like, as you remember the previous sessions, like in which we are taking a complicated hypothesis, suppose like theta 0,
Lot of betas will be there, right? Beta 0, beta
lot of
1.
betas. Okay, so lot of features which will represent lot of x. Okay, and corresponding lot of betas. Okay, and the data is not enough. Okay, so it will overfit, means like a complicated hypothesis. Okay, So that is the idea. Okay, and the rest of the derivation is in the videos. Okay, so you'll get the discriminant from the logit function, that is the probability of occurrence of the class divided by probability of occurrence of another class. Okay, and log of that, and simplify that, taking into consideration that this is a Gaussian distribution, that likelihood, you will find the expression of the discriminant or the decision boundary. Okay, in that, in as you are looking for the mean and the standard deviation, means like you have to maximize the discriminant. Okay, that is the actually the loss function here, and it will give you and find the value of the mean or standard deviation for which is it is maximized. Okay, so again, one thing to mention was that in this case, in this derivation, uh, as we are going through it, you have to consider the mean and like the standard deviation of both the classes, class data, that is we have considered Gaussian. Standard deviation of that will be same. Okay, that is the assumption in linear discriminant analysis, otherwise that it does not work well. Okay, so the question of the idea of this question is that same, as the standard deviation is same. So you see that this is like two-dimensional data. Okay, so standard deviation here represents the shape of the data. Okay, so as the shape is same, so they have the same standard deviation, and we are also trying to separate a class. Okay, and dimensional reduction. Okay, so we have to use the linear discriminant analysis. Okay, perfect case for this.
So in this case, what's the answer? Like we have two classes in our data set. The two classes have the same mean but different
No,
variance.
same variance but different mean actually. Mean, as you can see, the location is different, so mean is different. Okay, as you can see here,
Okay, okay,
this is the
okay.
mean here,
Right, right,
and
right.
this is the mean here. Okay,
Hmm.
these 2 points represent the mean here. Okay,
Okay.
and so okay, similar question actually. Two data set, same mean but different variance. LDA cannot classify them. Okay, has to be same variance. Okay, different mean. Okay, and so this is also means like the class condition probability density of each class is the likelihood. Okay, that is considered Gaussian in LDA. So like that, this is solvable. Okay, and the answer is also given. A different covariance matrix is estimated for each class. That is not correct. Okay, covariance matrix will be same. Okay, in case of means if the data is one dimensional, it is the variance term is used. If more than one dimension, then covariance matrix is used. So same covariance. Okay, same covariance matrix. And actually this part is a interesting one. uh, as you would know that on the decision boundary, means suppose this is the data we have, and this is the decision boundary, this is the different data on different side of the. Okay, so in the decision boundary, the class condition probability density means like these are equal or not. Okay, this is the idea. Okay, so let me show you. So here the what was the question? Let me see. Okay. So uh, the the decision boundary, that is like the ratio of the log of these two probabilities, okay, and it is put to 0, okay. So you'll understand that okay, let me show you here. So the log of this ratio, okay, for one class some expression of this divided by for another class some expression, okay, like this only. This will be same, so it will be removed, okay. Means it will it will cut down, okay. Only this f k1 x by k1 divided by f k2 x by k2 will be there, okay. And this will result into expression, okay, whatever it is. But as we are on the decision boundary, this has to be 0, okay, right? 0 or 0, right? 0, yes, has to be same, okay. So taking log anti-log on both sides, what will result, okay. So what we'll get is like, let me write it down. Yes, so what we'll get is fk1 x pi k1 equal to f k2 pi k2, f k2x pi k2, okay. So as you can see, this will be equal, but our question says that fk1 has to be equal to fk2, okay. So that is not possible, means maybe or may not be, okay. So how it is maybe or may not be, let me explain.
Because pi k1 and pi k2 may be different, right?
Yes, may be different or may be same, okay. So that is actually the idea, okay. And so another question here, okay. So there are two data sets. So read the question, right? So the idea is like, in one sample, means data is there. In another sample, means like, another sample also data is there, and the idea is that for class 0 there are 100 samples and here are 50, okay. And another data set, you have 100 samples but 50 is repeated twice, okay. Every sample is repeated twice, okay. So the idea is like, answer this questions, okay. So you will have to understand this, like, given the question, okay, the mean of the distribution in both cases will be same. Means I mean to say that, like, there are two different data set, okay. Okay, so I'm saying the mean of these two will be same and mean of these two will be same, okay. Because you can understand, in second case the like samples are twice, but there are the number is also twice, so in division it will be same, okay. So mean is same, and the variance of means the covariance of both has to be same here, as well as the data is same here, these two are same covariance, so this two has to be same as well, okay. So everybody has a same covariance, okay. And so the mean and covariance matrix is same, okay. And now what we have got is that, so the likelihood must be same, Okay, so let's go back to this. So the fx, okay, means what I mean to say is, for if you look at these two, okay, the likelihood of these two will be same, and different with this, okay, different with this, but means like same among these two, likelihood will be same, and these two will have the same likelihood, but these means that likelihood may be different among these two. Okay, I hope you understand here. And so what I mean here is, so so like you know that this will be ratio of the pi k fx and pi, and another like that. Okay, that will give the decision boundary. And as you see that fx, the ratio of fx will be same in both case, but the likelihood here means the prior can be different. Okay, okay, prior here will be actually different, because given the data in this scenario, the means the occurrence of this class is twice likely. Okay, prior of the data, we already know that means, as compared to this one, previous one, the data are occurring twice of this class. Okay, so from prior we know that this class is twice likely here. Okay, so what I was saying, okay, so so the second case, the pi of this pi means like in the ratio, the denominator pi will be double. Okay, and that will result in, if you see that, let me explain more actually here. So let's get another slide. So the our the discriminant will be pi k, okay, and multiplied f k, and for another class it will be pi k dash f k dash. Okay, so in log, this will be pi k divided by pi k dash plus, and this will give the linear part of the, linear means like x that will be there, and there will be some coefficient here. Okay, means you have seen the derivation video, right? So this gives the, by means the, what do you call this, so as you can remember, y is equals to mx plus c, so this is m x plus c, so this is the c part. Okay, that is the, what do you call that, just cannot remember the name, intercept. Okay, so this is the intercept. As you see the pi, this means m will be same here. Okay, because of same mean and covariance. Okay, but this part will be different due to different pi. Okay, the denominator pi will be different. In the second case, the pi k dash will be double. Okay, so they will have different intercept. Okay, and in the second case, the intercept will be divided by ln2. Okay, you can understand that more precisely. Okay, so different intercept, same slope but different intercept. Okay, this is the answer. Got everyone?
Can't we not derive that from the equation of that line, that omega t x plus b less than 0 and omega t? Like, in one case it will be uh, here omega t, omega transpose x plus b less than 0. In one case it's greater than 0. So slope is same. Slope is omega transpose only. Whereas intercept is, in one case b will be less than 0, one case b is greater or equal to 0. Something like that. No? So intercept will be different, but slope is same.
No, but the thing is like you were saying that yeah, just understand this one, okay? So what it is given here, x, right?
Sir, screen is not visible, sir.
It will be
Not
visible.
visible.
Okay,
Oh,
you have
okay,
some
okay.
lag, okay?
Okay, okay, fine. It's
Okay,
visible, sir.
okay. So the decision boundary is given. W is the slope, B is the intercept here, and this should not be x actually. Means like wrong question making. Why? Okay, it defines the class actually. Okay, not x. Okay, it has to be y. And so this is what it is saying. Okay, and but you must understand that for this case it is wb. For the other case, for the first case suppose it is wb. For the next case it may be different, w
Audio is
dash.
getting cut.
Hello, audible?
Sir,
Hello.
audible, audible.
Okay,
Yes, sir, audible, sir.
okay.
Yes,
For
sir.
for another
Yes,
case
yes, yes.
it may be w dash b dash. Okay, okay. So that as you're saying that w has to be same, from this you cannot infer that. Okay, maybe different. Okay, w is same because the mean and variance is same, mean and covariance matrix. That is why w is same. Okay, this is just a general statement that they have given. Okay, how to classify given this situation. Okay, that is the idea. I hope
Okay,
this.
but I did not really understand your explanation that how the two models will have.
What was your question?
No, like you explained something that, and you finally arrived that two models will have same slope but different intercepts. How did you
Yeah,
arrive?
it was because that that slope part is taken care of by the mean and actually I have written don't I have not written the full derivation. It is in the videos. Means like you can understand so much writing, and it's I don't have a writing pad as well. Okay, for now.
I think it's high time you get a writing pad because it's very difficult to read when you write like this, no?
Okay, okay. I'll be getting soon enough. Okay, and so so what I was telling, right? The idea is that in that means like let me show you actually. mm, Visible, right? Everything is visible. Okay, so as you can see here, this is the expression as that log of ratio of these two. Okay, this will be separated because of the addition means multiplication, addition log logarithm. Okay, and then simplifying you can see that uh, this this is the, you can see the screen, right?
Yes,
Okay,
sir.
yes.
Yes, sir.
Okay,
Yes, sir.
so the slope part is because of the covariance matrix inverse of that, and this mean. Okay, as these are same uh, in both case. Okay, so the slope will be same. Okay, but you can see the this term. Okay, in the intercept part. Okay, as they are different the intercept will be different. That is the basic theory. Okay, Okay.
Yes, sir.
Okay.
Okay. Let's move on. Okay. So uh, next, as you can see, the second option is very easy. As I have Fisher information result. This is the one. Okay, we're trying to maximize. There is another interpretation of the LDA. Maximizing direction of happened.
Sir,
Quitting the
which number question, sir?
uh this is one question, question number 9, I think.
Yes,
Let
sir. Which of the following statements of LDA are true?
Yes, I'm telling actually.
Uh, uh,
You can switch off the mic. So as you can see, uh, okay, here the derivation will be important, which I have not written here. Uh, uh, if you see the derivation, it will be simple enough actually. That is how this part was arrived at. And another is that minimizes the between class variance related to within class variance. Minimizes, yes, it minimizes, okay, between class variance, as close as possible, has it has to be, but within class variance, okay, it has to be low. Okay, it is also in the derivation, will be more clearly explained. I could not do that. Okay, it is in the videos overall. And which of the following statements are true for a binary classification problem? Acha. Yes, yeah. This is actually an important concept here. That is actually not in videos, or I was not told. But the thing is that uh, LDA is is means like prone to outliers. Okay, means if a outliers occurs, okay, what will happen that LDA will not work well. Okay, so what do I mean by that? But logistic regression actually works well even with means like more resistant to outliers. Okay, so the idea is of in the definition of LDA that the variance has to be same. Okay, suppose there is a outlier here. Okay, then the variance will then the shape will get something like this. Okay, so the variance will become different. Okay, that is why LDA cannot work well in this case. So adding a few outlier to the dataset is likely to cause a large change in the distance boundary of LDA compared to the logistic regression. This is one answer. Both algorithms learn the same decision boundary. That is not true, as means like they will both classify well given the data set has does not have outliers, but the still the classification boundary may be different. Okay, adding a few outliers to data sets cause that is wrong. Okay, logistic regression may still work well if the within class distribution deviates significantly from the Gaussian distribution. Logistic, like this one is also answer. Okay, this is also from the definition. The within class distribution, if it is not logistic regression, it is not a Gaussian distribution, then the LDA will not work, because in the definition of LDA, they have to be, the likelihood has to be Gaussian. Okay. Okay. So that is the idea for now. After break, we're going to take a 10 minutes break here. After break, we'll discuss about linear classification, uh, gradient descent, stochastic gradient descent, and let's see how much we can continue after that. Okay.
Sir, I have a doubt in fifth question.
Fifth question. Let's see.
Fifth.
Fifth here, not there. Which week actually?
The third week assignment, fifth question. Base
Okay.
classifier.
Let's see. This is the one, right? Yes. Fifth question. Okay. What is the doubt? Hello. What is your doubt?
Sir, if pi 1 greater than 2 pi 2, prediction could be class 1 or class 3. Is it the statement is true?
Yes, it is true.
Sir, there is no information given for class 3. Pi 3 for that class.
As I explained, like from this you can infer that, as I have told you here. Where is it? This is the one, right? So explained before as well. So like if it is twice, okay. So what will happen is, uh, means suppose this is twice, pi 1 equals to 2 pi 2, then first one we will have uh, 0.3 multiplied. mm,
Sir, it's okay. It's okay.
uh,
Then don't have any
okay.
information about pi
Yes.
3 equal to
Yeah. Yes.
9.2.
So that is the reason actually. So class 1 is greater than class 2. So class 1 is more likely to occur than class 2. Okay. But nothing is given about class 3. So it may also occur, means like suppose the class 3 probability exceeds the class 1 probability in some case, okay, as I have explained here. Okay. In this case 9 pi 2 it becomes equal, suppose like 9.5, then class 3 will be the answer. Okay. So it is not known because information about class 3 is not given. Okay.
So is that answer is correct?
Yes, it is
Since
correct,
there
because
is no
like here
information.
like maybe situation is there because of could be. Okay. Not sure. Okay. Maybe class 1 or maybe class 3. Okay. Got it.
Oh, okay, sir. But there is no information given about pi 3. So that I asked
So
that question.
no, that is why actually the answer will be that one, because if any information is given, then we can for sure say that it will be class 3 or class 1. Okay. Or okay, if any information is given, but as it is not given, that is why it is the answer. Okay.
Oh, okay, sir.
Okay, I will be back after 10 minutes. Okay.
Sir, week 4 question first. Anyone who knows week 4 question 1?
For question 1, let me take it. I think the answer is 1 for week 4, question 1. The answer is 1 because
Yes, I think also.
that is closest to the separating plane, no? So,
Okay, thank you.
Second question.
yeah, second
Any
question.
idea?
If anybody knows, please tell. Second question, I have no idea. Week 4, second question.
Is it k plus 1?
Hello. Anyone is having any idea for question number 6, sir?
I think for question number second, it's an K, sorry, because it is soft margin SVM with a linear kernel. Can anyone verify, please?
Can you explain how it is? Like, can you explain the equations behind it?
No, I don't have proper explanation, but it just seems that from intuition, I'm just saying like that only.
Hello everyone. Any doubt up to this?
No, please proceed.
Okay. Okay. So so we are going to learn about a optimization technique called gradient descent. Okay. So uh, previously you have seen that we have derived the closed form of the solution for linear regression. Okay. And and which was this x transpose x inverse, and what was the formula? Maybe this is the one. Okay, not here. That pseudo inverse formula. What was that? Y was here, and x was there or not? Okay, let me see.
Beta is equal to x transpose x, the whole inverse, into
Okay.
x transpose y.
Okay. Uh, okay. So so this is the one. Okay, to find the parameters of the regression, and the limitations of this is as you see, we have to find the inverse of this combination, this matrix x transpose x, and and which may take lot of time. Okay. So means computationally expensive if the size of x means uh, x is the that that feature vector, right? Vector matrix. mm,
Sir, can you solve week 4 assignment questions
uh,
similar type?
yes, but this is actually important to cover actually quickly. uh,
Yeah.
okay. So it is important because like solving the MCQs, you will not learn machine learning well. You need to solve means like you have to code actually means in this course you are not going to code. Okay. But as there is only MCQ questions, but it is important to code to implement these algorithms that you have learned. Okay. Linear regression model, logistic regression, you have to implement this on a data set. Okay. So the idea is that this if the size of this becomes too much, suppose 10,000, more than 10,000 cross 10,000. Okay.
It's very difficult to compute actually. This.
Yes. So the inverse will become very expensive. It will be time taking. You will not have the computational resource for that. Okay. And so that is the idea for, that is the pretext for coming to gradient descent. So um, it's like solving MCQs is a very shallow way to learn. Okay, machine learning, you have to code, you have to implement these algorithms. Okay, and gradient descent for that is crucial. So this is our suppose a function. Okay, a convex function. Okay, convex function we have. Okay, and as you can see, only I have one dimension in x. Okay, that is why it is portable in 2D. So the convex function, what it means is like a bowl shaped function. Means like, as you can see, uh, uh, means like if you pour water, it will fall into it, right, like that. So that is convex function. And means there are many mathematical better definitions. You can look it at optimization by Boyd. Okay, the lectures are here, maybe even in YouTube. Okay, better definition of here is convex optimization. Okay, so he's the pioneer in convex optimization. Gradient descent is only a small part of it. Okay, so this is convex function. Anything in which the minima, there is only one minima. Okay, and and uh, and like that. Okay, and no maxima here. Okay, so that is how it is convex function, smooth curved outward convex function. So our idea is to uh, reach to our global minima, that is this point, and for that uh, what we do is look at the definition of derivative here. Okay, so fx plus okay, so this is the definition of derivative. Suppose the fx is y here. Okay, okay, and so from this you can see that another slide, right? Okay, so from this you can see that we if we get to this, if we are looking for this, uh, okay, so fx plus e is a small change here. Okay, and it is equals to e times or maybe write like this, fx plus e times f dash x. Okay, so if we are moving to a, suppose fx is here. Okay, and we are moving little bit, suppose forward, means here. Okay, So here, so this distance is E here. Okay, moving by this distance forward, so our value of the function will become this. Okay, and as you can understand here that that we are looking for this minima here. Okay, and so what we do here is that to get to our minima we need to subtract some value, right, from the function value. Okay, so what we do, that we defined this f for something different x, suppose x dash, a new x, okay, will become equal to minus. Okay, so what does this mean is, to reduce I need to subtract. Okay, as we are going further towards the x, we are adding as the function value is increasing, but to get to the down we need to subtract, keeping that e value positive. Okay, so this is actually the expression for gradient descent. Okay, uh, maybe confusing here, so this one is maybe x naught, I will write okay, for some new x, this is going to be fx minus e times f dash x. Okay, here e is called the learning rate. Learning rate. Okay, clear up to this, everyone? Hello, hello, able to understand gradient descent? Clear? Okay, so this is when f is a function of x in one dimension. Okay, if multiple dimensions, what we are going to do is we are going to write the same expression for every dimension. Okay, just keep writing it down. Okay, and okay, another thing is like mm, okay, so forget the multi-dimensional part now, for now. So what we're going to keep, we have come to this lesser step. Okay, means fx value is less here, and we'll keep reducing such that we get to this minimum. Okay, okay, so the idea is also important to understand, is like this slope. Okay, slope here, and suppose slope here, these are very different. Okay, this is much higher value here, and this is much lower value. Okay, the magnitude is okay. So so uh, as we are at the higher part of the curve, uh, we are going to reduce a much bigger value of this. Okay, e times f dash x. Okay, given e remains same. So, okay, e times f dash x is going to a much larger value when we are away from the minima. Okay, but as we come close, it is going to become more and more small. Okay, so the idea is like that, we are taking a big step, it is small step, 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 and then what will happen is like the step is so small that it will means like uh, what do I say, like approximately approximately coming to this position, if you understand this. Okay, so what is going to happen, that it is never going to converge perfectly. Okay, but it is going to keep swinging at the last step. Okay, like this, not coming to perfect stop. Okay, and that is gradient descent. Okay, that is in one dimension of x, if it is. Okay, and suppose the dimension of x is more than 1, suppose 2, 3, or like that. In every direction we are going to write the same equation. Okay, so and if f is function of x in multi-dimension, it cannot be written like this. Actually, you have to write like this: del by del x. Okay, partial derivative in, suppose, del x1. Okay, in x1 component of x. Okay, x1 dimension, x2 dimension, x3 dimension, like that. Okay, so this is the, and for every dimension you have to write this. Okay, for multi-dimensional case. Okay, and and this is also betterly written as fx minus e times gradient with respect to x, fx. Okay, so what I am writing is like, this is fx I have. Okay, and the gradient of x is the derivative in every dimension. Oh my god, is the derivative in every dimension. So del by del x1. Okay, then del by del x2, del by x3, x4, like a vector. Okay, vector of that. Okay, so this is the gradient descent algorithm in multiple dimension. So what you are going to do is that, let me write down the algorithm overall. uh, okay, let's see. So the algorithm is that, uh, in our case, this function is our cost function, the loss function. Means in the case of linear regression, let me write it down. Okay, in the case of linear regression, it is fx is squared error function. Okay, so what is the meaning of this is, uh, when we are performing linear regression, what we need to do is minimize the cost function. Okay, minimize the loss function, and from that calculate the value of the parameters beta. Okay, beta values. Okay, and so that is the idea. Okay, and repeated application of the gradient descent results in the minimization of the cost function. Okay, and which will result into our best fit linear regression line. Okay, square error cost function in case of logistic regression, it is the MLE loss. Okay, squared error function is also we have got from the MLE only. but this is it. Okay, so okay, okay, a little bit wrong. Okay, got it wrong actually, sorry. Some message here actually. uh, yes, Urvashi, what is your doubt? Hello, Urvashi, any doubt? Hello. Okay, by mistake. uh Actually, I also made a mistake here, uh, and that is like this will not be f here actually, but x only. We're updating the, no, no, not x as well. Let me see. Acha, this is okay. uh, okay, but in our case, okay, that is means like in our linear regression case, or maybe logistic regression, means it is used everywhere actually. Linear regression, logistic regression, neural networks, SVMs, everywhere. Okay, so in our case it is like our parameter theta, uh, so our parameter, suppose theta or beta, whatever that were. Okay, means like I'm trying to say this one, uh, y is equals to theta transpose x. Okay, and in x the bias term is also taken, that is 1. Okay, that is also taken. So our theta vector, okay, theta vector is to be updated. This is the assignment sign in when we write pseudo code here. Okay, so that is will be our old theta vector minus gradient of the cost function, that is j theta, with respect to theta, and there is a learning rate e. Okay, so suppose you initialize theta to a, means when you start the algorithm, to initialize to a value theta 0. Okay, and then uh, you repeat till convergence. Repeat till convergence. Okay, so so this j theta is the cost function of linear regression, logistic regression, any cost function you might have. Okay, take gradient of that, that will be vector here. Okay, theta is also vector. Okay, and keep updating till we get to the till convergence. Uh, so the convergence, how to check about convergence? Okay, so the idea is that suppose in successive steps the difference between thetas, that is delta theta, is less than suppose 10 to the power minus 3. Okay, if the change is less than 10 to the power minus 3, then we say that converge, or like that. You have to means take a value to get the estimate. Okay, or maybe 10 to the power minus 3, 10 to the power minus 5, 10 to the power minus 4, 10 to the power minus 2. Okay, anything you are happy with. Okay, so this is the criteria for convergence. Okay, so what does this mean? As you have got to the optimal theta that you are looking for. Okay, and another is this learning rate is usually very small. Okay, on the scale of 10 to the power minus 3. What most people do is that if this is too small, then multiply it by 3. Okay, and if it is too small again, then multiply it by 3 again, that is close to 9. Okay, but that is 9, that is close to 10, that it becomes 10 to the power minus 2, like that. Okay, so start from 10 to the power minus 3 and keep increasing like this. Okay, if it is 10 to the power minus 3 is too big, it can be, maybe it start from 10 to the power minus 5, like that. You keep trying till it works. Okay, this is the idea of gradient descent. Everyone got this? Gradient descent, not too tough. Hello?
Okay, got it.
Got it, right? So this is the gradient descent. Okay, so do you want an assignment?
Yes, sir. Can you go through question number 6, assignment 4?
4th we have not done. Okay, support vector machines is harder to understand. Let's see. You have to code actually to use solve this question.
Sir, question number 6,
Achha,
not
6.
that one.
It will be harder to explain without explaining anything. SVM means, like, I was planning to cover linear classification today. SVM not today. Okay. Uh, the thing is, like, the gradient descent, like, you have to implement gradient descent as well. Okay. You understand? Like, you have to take a data set and run a regression problem, or uh, yes. So okay, if you can see here, that example that I have given, housing prices data set. Okay, and you have the data set here. Okay, how to make it small? Okay, so in this data set you have these parameters. Okay, the features are this. Okay, the x1 is like price of the house, area, y is price of the house, x1 is area of the house, number of bedroom, number of bathroom, number of house stories. Okay, like that, x1, x2, x3, x4. Okay, so there will be corresponding theta values. Okay, so you have to fit a linear regression model, that is y is equals to theta 0 plus theta 1x theta 2x. So like that, let me write it down. Take it as an assignment. Actually means, like, if you don't code, it's very hard to learn if you don't implement this. MCQs will not do the trick. Theta 0 theta 1 x 1, like this is the hypothesis. Okay, I have told you before, this is the hypothesis, like this, theta 2 theta 3 dot 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 dot. Okay, so this is the hypothesis, and you have the data set here. You have to run a gradient descent with the squared error cost function to get to the values of thetas. Okay, to get to the values of thetas, and that will be that will be the hypothesis, that is our model. Okay, which will be the linear regression linear regression curve that will fit through the data. Okay, so like please do that actually. Okay, solve this problem. Code is also given here, I think, solution code, but solve it yourself. Okay, lot of different techniques here. Okay, but use linear regression with gradient descent, and you can solve it with the normal equation as well. Okay, normal equation means normal equation will work as well. If we go above here, this is the normal equation here. Okay, you can solve it using normal equation as well, and solve it by both techniques. Okay, get the practice of this, and you can solve a logistic regression problem with this gradient descent as well. Okay, so are you getting this? Hello? Oh. Oh, what a problem. Hello? Hello everyone. What is happening? We got it. Okay, so please implement this. Okay, because it is important to code as well. MCQs are not enough. Okay, and and uh, and another acha another thing remains is like, as you can see here, so this is the gradient descent algorithm. Okay, but you have to understand that mm, yes, the thing is like you have to calculate this. Okay, gradient of j theta cost function. Okay, okay, you can calculate the gradient, or should I do it? Hello, anybody online? Hello. Okay, I think you can do it, right? Okay, so next we'll go to the linear classification and the concept of perceptron. Okay, so the perceptron is designed like this, defined like this, that is, not designed, so usually like this. Okay, perceptron is actually nothing but like these are the x values coming to this perceptron. x0 is 1. Okay, x0 is 1 here, and x1, x2, x3, x4, and this is theta 0, theta 1, theta 2, like that. Okay, and theta 3, dot 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 dot. Okay, and the output is our y, which is a classifier. Okay, and 0 or 1, or in this case you will see that it is easier to classify, means it is easier to understand the concepts I'm going to teach if y values are y 1 and minus 1. Okay, okay, and this is called a perceptron.
Theta i's are the weights.
Yes, so
Okay.
yes, so the what I'm trying to explain is like, and this a bias term is also there, means theta 0, I think. Yes, so what you can write is like this: theta transpose x plus theta, means like in this case I'm writing b here, bias term, and is this is the okay, our hypothesis. Okay, and the idea is 2y minus 1 let's see. So y will happen only, y will work. To 1 or not. Okay, so the idea is that this is greater than 0, right? I think so. Yeah, yeah, that's the idea. So the idea is that if this value, okay, theta transpose x plus b is greater than 0, then the y should also give the value 1. Okay, and if it is less than 0, the y should value give the value minus 1. Okay, so this is the idea of the perceptron. If I go more detailed into it, giving some examples, uh, uh, this is our data plane. Okay, this is this our data. Okay, this straight line. Perceptron always gives a straight line. Okay, this x values are all is there are no x square terms, x cube term like that. Okay, always a straight line to classify. Okay, and one more thing is like, you need your non-linearity in the form of that what do you call sigmoid. Okay, as well, for this to happen. Oh, no, sigmoid is not needed here. For now it is not needed. Okay, yes, this expression is correct. Okay, but to make this happen, means like to for prediction, for acting as a classification algorithm, there has to be the non-linearity over the hypothesis. Okay, so this will help in predictions. This will give the classifier. Okay, and so few examples have to be taken here. our AND. So this is called linear classifier, okay, because it is a straight line, so linear, and it's classifying between the two data sets. And or, okay, nor, or nor is not required.
Excuse me, in today's session, will you be covering anything other than this? Is this the last topic, or will some other topic be covered after this?
This is the last, but I will introduce SVM here, okay?
Okay.
Only introduced SVM, because it's important to understand the intuition here as well, because like SVM can be difficult to understand without the intuition part. This I can delete. Okay, so the AND is like this, okay, so we have x1 and x2 here, 2 dimension, okay, for x, and this is the y values that will occur. So x is 1 1, then y is 1. That is the definition of and okay, this has to be 0. This has to be 0, 1 0 0 0 0 0. Okay, so if we plot this here, this is the data set for AND. Suppose there is an AND gate, then this will be the data set looking like, okay, and I will use the 0 to represent the 0 values, okay, and 1 and cross for 1, okay, so 0 0 is 0, okay, so here this is also okay. So we need a classifier here to classify, to separate into two distinct regions, okay, this is this, okay, and what will be the equation of this? Can anybody say? Hello? Equation of this? What are you going to do to find the equation here? You can take it as a homework, okay, finding the equation here. So and or, in that case it is a linear classifier, okay, and for or also find the equation here, okay, and for equation what I'm considering is like you are taking this margin, there is a what I called margin, to be equal on both sides, okay, then only you can find the equation effectively, okay. So in and or, this is a straight line is able to classify, but in the case of XOR you cannot fit a straight line, okay. So XOR is this, so you cannot fit a straight line to classify this one, it is not possible, okay. So this is how the neural networks started here, when linear classifier, the perceptron, is not able to classify XOR data set, okay. So this is the idea of this, and if I write again, W transpose X plus B is the equation of the classifier. The distance means like this is the data set you have, okay. This distance means distance from this point, this one, you can, it is it is 1 by W mod, means norm. Okay, norm, that what you call L2 norm, okay, of W. Okay, this is the this value is called margin. Okay, and if taken on both side, okay, so you have to understand the distance from the nearest training example, okay, is the margin. So this is twice on both sides, okay, if taken from both sides. This is called the margin. Okay, and okay, this one is homework. Remember, it is important to calculate this one. I'll do it next time though. Equation of the separator, okay, linear classifier here. Okay, so this is called the margin here. and and so if we increase the margin as much as possible, so that our training examples are well separated by this distance, what it means is that we have a more robust classifier. What I mean by that is that uh, I can say for my confidence that data set that is in this region, I can say confidently that it is of 0 type. Okay, this is like X type. If the margin was very small like this or in the boundary, I cannot say for sure, I can make a mistake. Okay, with this margin as much as possible, I cannot make a mistake. Means my chances of mistake are, is the our model is more robust during test. Okay, it is going to make lot less error. Okay, so this is the idea of SVM.
Sir, I have a doubt. If I have an SVM classifier,
Okay,
and we take some features, and
some
if
I
it
could not understand.
to be some
Some what is it?
She said features.
Features. Yes.
features,
Okay.
we train SVM classifier with
Yes.
some features, and its performance is very less.
Okay.
Its performance is low,
Okay.
and if we add more features, then what about its variance and bias?
Bias and
Is it
variance. Oh, you have more features.
yes?
Okay. So as you can
Okay.
understand, like in the
Add
case,
more features to improve the SVM.
what do you want to do?
Add more features to improve the SVM features.
Acha.
SVM output.
Okay. So the idea is that with more features, you are going to learn better. Okay. Means like it is a
Yeah.
more. It has more capacity. What is called capacity? Capacity to learn. Okay.
She's asking the effect of bias and variance if you add more features.
Acha, bias variance is the same thing. Okay. As you add more features, the model becomes more complicated. So more variance. Okay.
And it will
More
lower the bias.
bias or variance.
Variance will be higher. Okay. Bias will be lower. Okay.
Sir, it is used. It is we taking more features to improve this SVM model.
Yes. So what you're asking for means like that. So
Then what will be the bias and variance?
bias will reduce and variance will increase. Okay.
Okay, sir.
Okay. Because
Okay,
this is
sir.
more complicated. Our that lecture you remember, bias variance I had told. Okay. Let me just show you it again. The theory does not change for any machine learning model. It remains same. Okay. So let me show you actually from the slide. In the meantime, let me introduce SVM here. So that is, let's go to right. Yes. So the SVM is the maximum margin classifier. Maximum margin means means as much as possible to maximize this margin 2 by W mod. And it is a hard margin, that is no training example should be inside this margin. Okay, all should be out of the margin, means on the right side or the left side, cannot be on the. There is also soft margin SVM, but we'll come to that later. Okay, so our idea is here we want to maximize the margin. So and this W the L2 norm is like non-differentiable. It is easy to understand. So you have to take the square of the L2 norm. Okay, and you have to take the, means like just okay, just means I'm trying to square of this L2 norm. Okay, and I'm going to minimize this one. Our ask is I need to minimize this to get to the SVM classifier. Okay, so this is our minimization problem here. And okay, so rest we'll cover in the next term. So this is the SVM introduction, that we have to minimize the this expression. Okay, and one question is already solvable here. Let me show you. So for two class SVM is there 4 instances of training data which will have the most impact. Okay, so these are the boundary. Okay, this is the okay, what expression it is, as I explained that W transpose W is the inverse of the margin. Okay, means like inverse means 1 by margin. Okay, so margin was maximizing the margin. Okay, and if I do 1 by of that, okay, upside down, then that is minimize the W transpose W. WL, that norm of W is not differentiable, so I took the square of the norm. Square can be written as W transpose W. Okay, so this is our problem statement of SVM. And the theory of it, from the theory of SVM, you can understand this the distance of this classifier from the data, the boundary will be defined by the data points that are closest to this classifier. Okay, so which point will have the maximum impact on the shape of the boundary? So this is one answer. Okay, simple enough, right? Okay, because one is the point that defines the margin which I am trying to minimize or maximize. Okay, if I remove the point 1 now, then it is going to define by some other point. Okay, so this is it, right?
What about the second one? Second one, it's related to SVM. Can you just
Second part is as second question, right?
yes, second question
Yes.
related to SVM.
Yes, so this is soft margin SVM. Okay, so soft margin SVM is like, if you can understand, means like it will tolerate training example inside the margin as well. This is the idea. Okay,
Okay.
other you can see from the videos.
No. But what does it mean? What does that second question? Can you just read it? I'm not able to understand. Soft match in SVM with a linear kernel and no slack variables trained on endpoints. The number of support vectors returned is k. By adding one extra point to the dataset and retaining the classifier, what is the maximum possible number of support vectors that can be returned?
For
Tuning
this you need to means study soft margin. Not possible like this. Okay. What how much you can do, you do yourself. Okay. We'll discuss next time. Okay. And the thing is like implement the algorithm gradient descent for linear regression and also logistic regression. Logistic regression, if I can find some problem for you, let's see. Can be like okay, just do the linear regression one. Okay, implement, it is important. Okay. Okay, thank you everyone. Thank you everyone.
Thank you, sir.
Yes, I hope you understood all. SVM we're trying to cover next. Okay, so homework is like that implementation of gradient descent and normal equation, and also write the yes, also find the expression for the linear classifier for and or gate. Okay, these are the one. Okay, thank you. নিজে পড়ে গেছে আর কি, সেটা পরে পরে জড়িয়ে